So it is our great pleasure to have Professor Jessica Hullman join us to give a lecture to our HDSI seminar. Professor Jessica Hullman is an associate professor of computer science at Northwestern University, where she co-directs the Midwest Uncertainty Collective, a lab devoted to modeling and visualizing uncertainty for decision-making from data. Her research looks at how to design, evaluate, coordinate, and think about visual representations of data for inference, decision-making, and communication, and has contributed uncertainty visualization techniques and theory experimental results of visualization-based decision-making and design frameworks and automated approaches to communicative and responsive visualization. Jessica is the recipient of a Microsoft Faculty Fellowship and SF Career Award and multiple best papers at top visualization and human-computer interaction conferences. So without further ado, let's join us in welcoming Jessica.
Thanks, yeah. So thanks for the introduction and thanks for having me. I'm excited to talk to you all. So my research interests, as Jan just described, revolve around the role of data in judgment and decision-making, and in particular, visualization interfaces have always interested me because they directly influence how we interact with and make decisions from data or predictive models in so many settings, from daily life to business intelligence or government policymaking to the scientific literature. And in these various settings, we often prefer visualizations for interacting with data because of this ability they have to offload cognition to perception and make it easier for us to identify patterns and relationships. So for instance, Anscombe's quartet, which maybe some of you have seen before, is this set of 4 data sets, which would look identical if we were to summarize them using stats alone. So if we looked at mean and variance of X or tried to run a regression, we get identical stats. But then when we visualize them, they're clearly quite different. We have outliers in some, we have different types of trends in others. And so in the last few decades, research on data interfaces, including interactive visualization, has broadened from addressing analysis only to also consider communication and decision-making under uncertainty. And yet, I would say when it comes to how we view sort of the real function of visualizations and visualization systems, even in research today, I think we usually put pattern finding at the center of how we see the value of visualization. So if we look at the state-of-the-art systems being created today, our design ethos seems to be driven by what we could call behavioral optimization. So we're simply trying to make the data easy to see and very easy to access so that the user can find the patterns. So we see this in advances like visualization recommender systems that suggest views based on perceptual or statistical features, behavior-driven recommendations that use low-level interactions to try to predict what the user will want to see next, and different types of multiple modalities for interacting with visualization, from touch to pen displays to speech and natural language driven displays. And all of these sophisticated types of behavioral optimizations would seem to assume that all we really need to do is give people access to the data and create tools that'll serve it up as quickly and as clearly as possible. And then we can assume that the human users will know what to do with it. They'll be able to find the patterns. We don't need to know about what their larger goals are, how they're trying to use data in some bigger decision process. We just want to serve up the data quickly and as efficiently as possible. And this notion, that visualization is really just about exposing the data and exposing the patterns, I think may largely be a carryover from the way interactive infoviz was born as a discipline, where we were largely inspired by pioneering efforts of statisticians like John Tukey, who popularized this idea of exposure, or using graphics to try to understand what's in our data, to find patterns before we even know what to look for. So Tukey talked about how graphs help us see what we didn't expect in this exploratory data analysis process. And I think this might have encouraged this pervasive view that exploratory data analysis, where we tend to use graphs heavily, is mostly model-free or non-probabilistic. So exploratory data analysis has this, emphasis on hypothesis generation, and this is difficult to reconcile with other forms of statistics, and in particular, statistical modeling and testing. It's not clear whether all of the activities that we do in exploratory analysis when we're looking for patterns and generating hypotheses can really fit within a more probabilistic framework like we think of when we think of statistical testing. And so today, perhaps because it's hard to reconcile these things, and because it's easy to sort of assume that Tukey just meant we should just be looking for patterns and think of visualization as just good for finding patterns, I think we see these tendencies in research to just sort of focus on that aspect of visualization's function. But, I think that our notions of pattern finding remain vague. And as a result, sometimes the tools we build based on this design ethos have some blind spots. So one example of an issue that crops up relates to things like how the defaults that we build into visual analytics tools can push people towards making sort of mistakes in inference. So many systems for visual data analysis like Tableau will aggregate data by default to enhance pattern identification when you have large data sets, millions of rows, But when people and businesses are using these types of tools to analyze and communicate around small data sets, which I think, happens a lot, they can run into trouble if they don't understand, for instance, what aggregation does to their ability to reason under uncertainty. So a couple of years ago, we did a study where we asked novice analysts to generate observations about a population as they looked at visualizations of a sample from that population. And we showed them either views that were aggregated by default, as in Tableau, or views that were disaggregated by default. And we, asked them for these observations. We recorded their confidence in the observations. We varied the size of the data samples that we gave them. And what we saw was that when people are shown aggregated data, these novice analysts, they tended to reason more dichotomously about differences they saw in the data. So this means things like they would say, oh, there's a difference between these two ad campaigns, or there's not a difference between these two ad campaigns, or there is a trend here, or there's not a trend. But they wouldn't really talk about, effect size. What's the size of the effect relative to the amount of uncertainty in the data? People did this much more when they saw disaggregated data. We also saw people's confidence in these kind of generalizations they were making about the population from aggregated data was less likely to be affected by the size of the samples they were looking at, which is also problematic. We want people to be responsive to the amount of data as well as just what patterns they think they see, because if you see a pattern in small data, you can't really trust it to the same extent. And so the goal of a lot of my work has been to try to find ways that we can ground interactions with data in theories of statistical inference and use this to build better visualization tools. So, we need to help people see patterns, but we also need to help them understand how well those patterns generalize so they can make good predictions and decisions from their data. And so today I want to just motivate why I think a lack of theoretical grounding and a tendency to not want to model, people's larger inference process can cause problems. And to do that, I'll look at one particular area I've worked a lot in, which is uncertainty visualization. And then I'll talk a little bit about kinds of theories of statistical inference that I have found helpful for structuring how I think about visualization and kind of what implications these have for how we build tools. So back as a PhD student, I became interested in this topic of uncertainty visualization. And I wondered, why is it such a niche area compared to sort of mainstream visualization? Because, in many ways, anytime we're visually analyzing data, we are on some level reasoning about uncertainty. And so initially I became interested in the limitations of sort of existing conventional visualizations for uncertainty, or more generally, what I mean by that is just ways of visualizing distribution. So many of these are static, and we see either techniques that use summary marks or graphical annotations to present statistical constructs or properties of a distribution. So things like error bars or box plots. Or on the other hand, we see people mapping probability to some visual variable or retinal variable like color value or width or opacity. And the problem with most of these techniques is that when we apply canonical criteria for evaluating whether the way we visualize data is successful, we see obvious problems. So for instance, with summary marks, they create what we could call expressiveness issues for many viewers, which just means that people tend to make inappropriate inferences based on the way that the error bars look. They convey some false information to people. So for example, this includes things like what we call within the bar bias, which refers to how, a decent chunk of lay people, about 30-something%, appear to think that the region of values that's on the lower half of an error bar is more probable when they see an error bar on a bar chart. And it kind of looks that way. It looks like there's some difference. We also see things like deterministic construal error, where if we're putting, say, an error bar on information or predictions in a certain domain like weather, people will instead interpret it as something like the low and the high value. So things like, a confidence interval on the predicted high temperature will be interpreted as actually the daily low and the daily high. And then, we see lots of problems, even with people who should be experts who are using, error bars and confidence intervals in their own research. We see these problems with properly interpreting the underlying statistical constructs. So studies have found, for instance, that psych researchers and grad students don't understand how 95% confidence intervals relate to statistical significance. And it's kind of understandable. A confidence interval is this hard thing to understand. On the other hand, when we map probability to visual variables like opacity or area, we can run into problems with what we call effectiveness in visualization research. The problem is that, we only have so many different visual variables or channels that we know that people can read data from very accurately. So position, things like scatter plots use our best visual encodings. We can read the data pretty accurately. But often we want to use these higher ranking encodings based on graphical perception experiments to show the data itself. And when we want to show something like probability, we're left with these lower ranking encodings. So things like, area in a violin plot, much harder for people to, for instance, like say, what's the difference in probability between two values, along the y dimension of that plot. And even worse is that, sometimes the encodings that we think look the most like uncertainty, things like opacity or blur used to map or being mapped, probability being mapped to those are the worst in terms of people being able to actually read the values back. So that kind of defeats the point. And so based on kind of understanding these problems, a while back, I was still a PhD student, I started to work on this idea of frequency-based uncertainty visualizations as one way that we might be able to sort of counteract some of these challenges with uncertainty visualization. And I was motivated in part by this robust finding from cognitive psychology from Gerd Geigerenzer, that in some cases we can re-express probability as a frequency, and we see that people do better in terms of things like classic Bayesian reasoning tasks. And so the idea is that rather than saying 30% when you're describing some event's probability, you might say something like 3 out of 10 times. But nobody had applied this to visualization. And so frequency-based visualizations of uncertainty will apply this discrete or frequency framing to try to make the visualization of uncertainty more concrete and potentially more useful to people. And there's a few techniques that I've worked on. So one variant that's closer to sort of what we might think of as conventional representations for distribution, things like density plots, is what we call quantile dot plot, where we're sampling proportional to the quantiles of the distribution. We choose some number of dots ahead of time, like 20 or 50 or 100, and then each dot represents some number of outcomes that you might observe with a certain value. So here we're using it to show uncertainty in bus arrival times. And the idea is that the visual system, especially when you have a small number of dots, is actually pretty good at estimating without counting how many dots there are, as long as the number is pretty small, like less than 5. And so, if I'm trying to estimate, what's my chance of missing the bus if I get to the stop in a certain amount of time, like 8 minutes, people could use these things and they didn't have to do the harder area estimates. They could be a little more precise in their probability estimates. Another technique that's a little more out there that I worked on back as a PhD student, and which I still like, is called hypothetical outcome plots. And this is a little more generalizable in that the visual encoding we use isn't necessarily fixed. So we don't have to constrain ourselves to simple 2D statistical graphics. We can take any visualization where we want to show uncertainty. And what we do is we take the distribution, the joint distribution if we have a multivariate visualization, or just the single distribution if we have a univariate visualization, and we randomly draw samples from that distribution, and we show each sample as a frame in an animation. So someone kind of watches the uncertainty play out over time, and as they're trying to estimate things like trends, they cannot help but take into account the uncertainty. So we've applied this to various difficult cases where you couldn't really just add an error bar or add another encoding, things like visualizing uncertainty in community membership predictions in network diagrams, spatially interpolated maps, choropleth maps, all of these cases where it's currently hard to visualize uncertainty. And of course, in doing all this work, I had to grapple with how to evaluate these new techniques. And so over the years, I've started sort of realizing that it's really hard first to evaluate uncertainty visualizations. And a lot of what people are doing in the literature is actually pretty obviously non-optimal. So a couple of years ago, I evaluated or looked at about 90 experimental evaluations of uncertainty visualizations, looking at kind of what behaviors people were setting out to change with the visualization and how they measured success. And I found that the vast majority of evaluations are actually just looking at how accurately people can read information from the data or how satisfied they feel when they're using the visualization. But if we think about it for a minute, there's no guarantee that just because I can read the data when you ask me in an experiment, I will also use it to make a decision. And also, there's no reason to think that people know what's good for them. Just because I like a visualization of uncertainty, I may not actually be helped by it. And a great example of this, I think, is if you remember the animated needle that the New York Times rolled out in election night 2016. A lot of people hated this visualization because it made them grapple with uncertainty, and they hadn't had to do that. But in actuality, it was kind of an effective uncertainty visualization. And so it's hard to evaluate these things. And in particular, one thing that drew my attention was that we know very little from the studies we've done about how people are making judgments and decisions from visualizations. And so with uncertainty visualization, we need to understand what people are doing, because we know that there is this tendency often to satisfice or use heuristics. And so in some of my work on these frequency-based visualizations, I started to look at this generic, but what I thought was an important type of judgment that people make, which is how they perceive effect size. So effect size means, given two distributions, we care about sort of the difference between the means of those distributions, but we want to normalize that by the pooled standard deviation. So it sort of captures when we have, say a control and a treatment, we can think of this, these are our two distributions, it captures how effective really is this intervention. And it can also be defined as what we call probability of superiority, or the common language effect size, which is the proportion of time or the probability that a random draw from one distribution will be higher than the random draw from another. So the probability that the intervention will actually have a higher value than the control. And so effect size judgments happen all the time. They happen with visualizations, even if we don't realize that's what we're doing. We're looking for sort of signal relative to noise. And the questions that I've had in doing this work is, well, how well do visualizations support them, and how are people making these judgments? And so in my original research on hypothetical outcome plots, the first paper I did, we looked at how different uncertainty visualizations impact effect size judgments, this probability of superiority. And one of the things we found was that while people did this better with the hypothetical outcome plots, when they were using, these more conventional representations, things like violin plots and error bars showing a predictive interval on each distribution, they seemed to be using this strategy that was really sort of just based on the visual distance that they saw between the means of the two distributions. So we'd ask them, what's the probability that the value for B is greater than the value for A, if we were to randomly sample from each? And if it was a small difference between the means relative to sort of the total distance set up by the chart, people would say, oh, it's a small probability, or it's a small effect size. And if it was a larger difference, they'd report a larger effect size, regardless of the amount of variance in each group. So they were insensitive to variance and sensitive to these like visual distances. And this heuristic ended up also being consistent with evidence we found a few years later that perceived effect size is reduced if we rescale the axes on a chart where we're showing 95% confidence intervals to match the full range of predicted outcomes. So, here we have, 95% confidence intervals. We did an experiment where we showed people intervals. We asked them whether they wanted to invest in this intervention, a special boulder in a boulder sliding contest. And we showed them either 95% confidence intervals, 95% prediction intervals, so the underlying measurement uncertainty, or the confidence intervals, but with a rescaled axis to show the full range of measurement uncertainty. And what we found is that you can change how big people think the effect size is simply by rescaling the axes. And so this suggests, people are relying somehow on visual distance, even though that's not necessarily optimal in many cases. And so the most focused study we've done on this topic won a best paper last year at Viz. It was led by my PhD student, Alex Kale. And we wanted to explicitly test, how much evidence there seems to be for users relying on the distance between distributions as a proxy for effect size. Because, like I said, effect size judgments are very common when we're looking at uncertainty visualizations. It would be useful to know, how good are people at this versus how shallow are their strategies. So we did a mixed design controlled experiment on Mechanical Turk for this, where we showed people, distributions with different levels of variance. So either at lower variance or higher variance. And we created these so that at low variance, the distances between the distributions, like this top row here, are going to look small regardless of the actual underlying effect size. That's because the scale is much larger than the actual variations in means. But on the other hand, at higher variance, distance becomes a better cue for effect size. And so by setting up an experiment where people saw these different stimuli, we wanted to test, how much do they appear to rely on this heuristic? And for this type of test, we can try to get at whether people are using this kind of heuristic by defining the expected pattern of responses if they were only making judgments of effect size from this distance between means. And we can do this as a function of ground truth effect size. So basically, we have these curves that we want to fit to people's decisions as they use uncertainty visualizations, where we're looking at how their response, the probability of superiority or the effect size they report, varies as a function of true effect size. And we can say that, at low variance, using a common scale, like I just showed you in these graphs, we would expect responses closer to 0.5. So people, if they're using this mean distance heuristic, they should be sort of underestimating and overestimating effect size, but more or less, keeping around 0.5. So they'll be pretty insensitive. On the other hand, at higher variance, if they're using this mean distance heuristic, we expect something a little closer to the actual ground truth, because effect size is a better cue in those stimuli. And here, the diagonal would be perfect. So we wanted to look at these curves and estimate the amount of bias from this heuristic. And in order to try to encourage the heuristic in the experiment, we also created stimuli to vary whether or not the means in these visualizations were salient. So for certain uncertainty visualizations, things like animated hypothetical outcome plots, it makes a big difference potentially in how I interpret the visualization if you show me the mean explicitly versus you make me try to estimate it. So, if I don't have to estimate the mean, or if I don't have it there, to see, then I might not rely on a mean distance heuristic. Whereas for other visualizations, we can add the mean as an annotation, but it's going to look much more similar to the original visualization because the central tendency is already visualized in a way that's sort of intrinsic. So things like probability densities and quantile dot plots. And so we hypothesized that in certain cases, adding the means, across the board, adding the means would make people more likely to rely on this strategy. But in particular, we should see a big difference with some of these visualizations, like hypothetical outcome plots. And so people in our experiment did some tasks where they had to estimate effect size, and they saw one block of visualizations where the mean was added and one block of the same visualization where the mean was not explicitly marked. And we looked at how well they did. And the task here was modeled after a fantasy sports game where we're going to ask them to judge, whether or not they want to invest in a new player, where they're trying to win an award. If they get a certain number of points with their fantasy sports team, they'll win an award, but it will cost them money to invest in the new player. And so for each trial, we asked them both for this effect size judgment, probability of superiority, but we also asked them to make an incentivized decision about whether they would pay for the new player or not. And we defined the incentives in this experiment so that, we could basically define the optimal decision. And we wanted to see, both the bias and effect size judgment from using this heuristic, but also how that might bias decisions. And we also wanted to just corroborate sort of what we thought we saw in the data in terms of reliance on this heuristic with what they said they were doing. So we also asked them to describe the strategies they were using to make these judgments and decisions. And so the results, I'm going to skip over a lot of the modeling details, refer you to the paper, and skip over some of the lower level findings, but just summarize kind of the high level findings here, which are about, this mean distance heuristic. And what we found was that if we added means to the plots, we did see this small effect on probability estimates that was consistent with people relying more heavily on the distance between means when the mean was annotated. But what was surprising to us was that this effect was very small. And it was very small even for visualizations like hypothetical outcome plots, where we had thought that if we add the mean and make it really, visually salient, people will totally switch their strategy. It did not appear to be the case. We also looked at, how they reported making these decisions. And we found there that, many people reported relying on this mean distance heuristic, whether or not the means were annotated. And I think I skipped something here. My slide changed too quickly, but we also saw the same bias in decisions where, if we added the means, people made decisions in a way that was more consistent with this heuristic. but it was a very small effect. And so what we found by looking at these strategies is that people appeared to be using this simple, shallow distance heuristic, whether or not the visualization showed the mean, and whether or not the visualization actually gave them much better information to make the same decision. So things like hypothetical outcome plots gave them the probability of superiority, or gave them a way to estimate that directly by just watching the animation. And yet people were still using these shallow heuristics. And so the results of this, for someone like me who has studied a lot of uncertainty visualization, were kind of sobering, in that they made me start doubting, how well the average person can really make judgments under uncertainty from visualizations, even visualizations that we think we're designing to be sort of optimal for these kind of judgments. And so, left to their own devices, people will try to extract signal and ignore uncertainty in ways that are kind of cognitively easy for them. And so this got me thinking, how do we design in ways that get people to move away from this? It's obviously not as easy as just proposing a new uncertainty visualization that should work. We also have to maybe think about, how are people actually doing inference with visualizations? What strategies are they using? And we need to maybe define what is normative, statistical inference with the visualization, so that we can better catch these types of cases where people are not doing at all what we thought they were doing. And so this got me into thinking about, well, what are underlying theories that we can use to think about how people are using visualizations to do statistical inference. And so 3 or 4 years ago, I started thinking about how Bayesian theory can be generalized to help us think about learning from visualizations in analysis. And initially, I got into Bayesian cognition, which has been explored a bit in mathematical psychology, with my former PhD student, Yesil Kim, and my current PhD student, Alex Kale. And so we've been using these Bayesian models of cognition to look at how well people seem to update their beliefs given visualized data in a variety of settings, things like estimating parameter values from data, like estimating, what's the rate of a disease given some data that I'm shown, but also things like judging the likelihood that different causal models might have generated some data that we show people. And so in this experimental paradigm, we're going to either elicit people's prior beliefs, things like, what do you think the rate of dementia in the elderly is in the US? Or we're going to endow prior beliefs, give them prior beliefs. And then we're going to show them some visualization that should give them information about the likelihood of different values of that parameter. So things like visualizing a big survey result, talking about the rate of dementia in assisted living centers. And then we're going to elicit their posterior beliefs, and we're going to compare their posterior beliefs to the expected posterior beliefs from a Bayesian agent who, followed a simple model and just updated the prior given the likelihood and arrived at some posterior beliefs. And so this gives us a way to sort of judge how well are people reacting to data using these simple models. And so we did it in several large experiments on Mechanical Turk, where we were varying the parameters we asked people about, the size of the data sets we showed them in the visualizations, and how we visualized the data, whether or not we made uncertainty salient. And we learned a lot from this. So in particular, we all have heard of things like belief in the law of small numbers. And we found, yes, people have this sort of tendency to over update a bit when they're shown small samples. But we also saw this much bigger problem where people were under updating their beliefs given large samples. So we'd show them a huge visualization of a huge data set that should sort of, dwarf their prior beliefs, and they should update quite a bit. But in reality, often people did not update nearly enough. And we could visualize uncertainty in more salient ways, and this helped a bit. But we still saw this sort of average bias in just like being pretty insensitive to the amount of information you get from a big data set. And there's various reasons in this that we can explore in this kind of framework. So we began thinking about, well, is it sort of a distrust of the data source, and can we somehow quantify that? Or is it something like, perceptual bias, like logarithmic perception, or a cognitive bias? And so this kind of framework gave us a way to just get a lot more precise about what we might expect to see and what we're not seeing, and try to tease this apart. Another place where we did this in a paper recently led by Alex Kale, we used a different variant of a Bayesian cognition model in order to look at how well visualizations helped people make causal inferences. So here, we gave people some data, and we asked them to think about several possible causal models, causal DAGs, or you could say, that are potentially could have generated that data. And we varied how we visualize the data. We include a lot of common charts that you'd find in like visual analytics tools. So things like static bar charts that are kind of equivalent to contingency tables, tables of icon arrays, interactive bar charts, and collapsible tables. And we asked them to allocate probability across these different models. And again, the results were surprisingly sort of bad. People did not do well at this task at all. They again were insensitive to sample size quite a bit. They were more sensitive to information that falsified or worked against a certain causal explanation rather than information that supported a given causal explanation. And what we found was that the visualization choices didn't really matter much. And none of the visualizations really helped people much more than a simple contingency table, like a text table. And so again, from this framework where we get a little more specific about normative inference and what we might expect to see, we can learn a lot about like what's not working with different visualizations. And so this line of work kind of got me reflecting on visualization and its function. And it made me start considering in particular how we could relate Bayesian inference to different phases of data analysis in a more general way, thinking about how visualization relates to learning as we're doing data analysis to see if it maybe would give me new ideas about how could we design visualization tools to be less hands-off. How do we help people do better inference given that we see these major problems where they're not learning from data as much as they could? And so related to this idea of Bayesian cognition, people updating their beliefs as they see data, about 20 years ago in the stats literature, Andrew Gallman, a Bayesian statistician, proposed that this idea of a model check could unite exploratory and confirmatory data analysis. And this is an idea that always seemed powerful to me because it generalizes across different phases of analysis. So the idea is that a good graph helps you check your intuitive statistical model, kind of similar to how, if you actually ran a statistical model, you might check the fit, check the results. And so here, again, this general idea is that people have kind of an intuitive statistical model that they're checking when they make graphs. And the graphs help them realize like where their expectations or where their beliefs were wrong. And then they might go on and create more graphs to sort of refine this mental model they have. So for example, if I'm a real estate agent, I might have some public housing sale data in my area. I might construct plots like the one you see on my slide and using something like Tableau. And I might ask myself things like, well, is there an effective neighborhood on sale price of the house? Or how's this relationship between lot configuration and sale price affected by neighborhood? Or, how well do above ground square footage and bedroom space predict what a home will sell for? And in all of these cases, you can think about sort of what I might expect to see if there was a big effect of some of these factors. And I can sort of, you can imagine I'm implicitly comparing that to what I actually see. So things like I might be looking for a smooth color gradient as well as some trend between X and Y in the last plot here. And so the general idea is that, visualizations help us check these internal sort of models or expectations we have. And we can make visualizations more useful by designing them with a notion of what the model that needs to be checked is. So things like histograms and bivariate scatter plots are useful because all we have to do is look for deviations from symmetry, which the visual system is very good at. So I imagine things like bell curves, and I can compare my data to that. If I'm looking at like a scatter plot matrix, I'm probably implicitly comparing to just a straight line representing perfect linear association. And some of the most effective plots that we see for formally checking model fit really are designed so that the reference model is essentially built into how the plot works. So for a residual plot, we want to see that the residuals kind of bounce randomly around the zero line. They should roughly form a horizontal band. And again, all we're really looking for is deviations from symmetry. So you can imagine, whoops, my slide animation is messed up. I have this notion of what I should see, and I'm mentally sort of judging what's the deviation. Here I might just look at like what's the bias, so how much is the horizontal line off from center, and then maybe as the result of my visualization judgment, I'm appraising, well, how big of a bias is this in my residuals relative to some distribution of bias I might expect. So almost like I have a p-value I'm generating in my head that tells me how important what I just saw is, how important this pattern or this deviation is. And of course, not everyone will do this in the same way. And in some cases, people might do things that don't fit this description. So things like using heuristics, like I talked about, that are not even, you can't even really call them an implicit model because They're not really generative. But the idea is that, this is sort of a useful approximation, thinking of people doing model checks that we can then try to use to help us understand, well, how might we help people a little more when they're doing inference from data? I'm going to skip over details here. So in a recent paper, we borrow from an older formulation that Hullman did, specifically talking about how this implicit model that someone's comparing to visualized data can be thought of as like the posterior predictive distribution in a Bayesian workflow. But I'll skip the details. But basically, the point is that we can actually sort of formally specify this and then try to take this model and begin to compare it, like I did with the Bayesian cognition stuff, to what we see people actually doing. But the big sort of picture is that we want to do this kind of thing so that we get ideas for how to make visual analytics software better. And so, if we assume that this idea that people are often implicitly checking model when they look at graphs is true, then, what does that tell us about how we can make software functions that better support these checks? So there's a few things that come to mind right away that don't even involve having to sort of have any kind of modeling going on, or having very light modeling. So things like we should probably default to presenting raw data, and probably default to representing uncertainty whenever someone's looking at things like averages. Because if people are doing this sort of Bayesian process in their heads, we want them to have a good sense of the likelihood of different parameter values. So, uncertainty should be the default in a tool like Tableau. Another is that, well, if we think that people sometimes bring prior beliefs to data and that impacts what they get from the data, perhaps we should have tools that allow them to specify those beliefs and help them understand, given your belief distribution, how much should you update given this data? And so there's these ideas that come up along those lines, but the harder thing potentially is how do we integrate sort of model checking in a way that makes the models more explicit in a kind of Tableau-like visual analytics tool where, we're trying to keep things easy. We're trying to let people just sort of drag and drop and generate a lot of visualizations. How do we also get them thinking about implicit models without overwhelming them? And so in a current project led by my PhD student, Alex Kale, in collaboration with Jeff Harrer at University of Washington, we're developing a Tableau-like visual analytics tool where people can interact as they do in Tableau. They can choose different fields and drag them to rows and columns. This will generate visualizations, but then we also have a model specification backend, which recommends models to the viewer that they could check against the observed data. And the idea is to make it more explicit, what they might be learning from different visualizations and to close this gap between sort of pattern finding and modeling. And so, we have sort of a drag and drop interface. You drag, things to rows and columns. You can manually specify charts by saying, I want this field on X, I want this field on Y. And then they get a visualization, but then this model engine is going to, work in a couple of different ways to surface models to check against their visualization. So we want something where, they can specify their own model if they want, but we're really going for also users who are maybe not comfortable specifying models, writing, R style statements. And so we want to think about, well, what are the models that we might recommend given a visualization specification? And sort of the core question behind this is then, well, how do we frame this coupling between a model and a visualization? And there's a few ways we can do this. So on the one hand, we could assume that for any visualization, there's some relatively unambiguous statistical model corresponding to that visualization that someone might want to check. So here my model is taking into account log of the area burned. This is forest fire data. I have a bunch of forest fires. I'm seeing, how much area was burned on a log scale. And I'm also looking at day of week because that's what my visualization shows. It looks at this area by day of week. And I can look at this plot and I can try to see, well, are there any discrepancies between these red posterior predictive distributions from a Bayesian model that the tool recommended to the user? And if I see discrepancies, I might, decide, oh, I want to add some extra variables to this plot and maybe see if I can explain any deviation here. Another example of how we might just take the visualization and try to infer the relevant model here is dealing with sleep data. So you could imagine an analyst is looking at some sleep tracker data. They might have things like hours of sleep per night and be trying to relate that to things like fitness levels of users of the tracker, or whether or not they've used sleep trackers in the past, or maybe their reported sex. And so, if you see someone using an analysis tool, making trellis plots, maybe adding lines of best fit, the tool might infer that they're doing something like checking for main effects and interactions of these variables. And maybe, we want to show them some draws from a model that's basically fit to the structure of the graph. So here I might see predictions from baseline linear model regressing, hours of sleep on sex and prior use of sleep trackers, and binary predictors as binary, and then fitness level as quantitative. And I might, for instance, notice that, oh, I thought I saw maybe a slight difference in kind of like the slope of one of these lines relative to the others, like the direction changes. But maybe if I saw predictions, I'd be less likely to sort of trust what I see from the raw data, because I'd realize, oh, actually, this is very uncertain. Like these model slopes can't be trusted because there's just not enough data. But on the other hand, maybe sometimes the more useful model to show someone as they're doing visual analysis is not the model that's sort of directly implied by the visualization they're working with, but instead an adjacent model. And by that, I mean, we might want to try to figure out what's the model that's sort of closest to the visualization, and then take one step away from that. So we're actually adding a variable that's not shown in their chart, or maybe even subtracting a variable that is shown in their chart. So for instance, even if I'm visualizing, data by month and trying to predict area burned by month, what would it look like if I didn't include month in my model? That might be useful for me as I'm sort of implicitly trying to reason about, like which factors are most important in predicting forest fires. So I can see sort of if I add this variable, what if I were to also add temperature? Do my predictions get even better? So this is kind of an exciting new direction we're exploring. We're still kind of building the system, but I think, it's exciting because it brings this sort of internal kind of model check thing that people might be doing into like a visual analysis tool. Of course, there's lots of challenges. So for instance, how do we ensure that an implied or adjacent model that we want to fit and show someone predictions from, how do we know that we can fit that? We need tractable sort of analytical solutions in most cases. And also, how do we help users, especially those who are not sort of used to doing model checking themselves in tools like R or Python? Like, how do we train them to recognize model misfit so that they get more kind of understanding about the underlying processes that might have generated their data as they're looking at it in something like Tableau? There's also questions about, how do we avoid overwhelming people? It's already hard to do visual analysis. Like, how do we make sure that we're not overwhelming them completely by showing them, potentially relevant model predictions? And then there's also ways you could customize this to make sort of the use of a visual analysis tool even closer to like a Bayesian workflow. So things like, can we elicit their prior beliefs? Can we let them customize different models that maybe the system automatically recommends? Do things like prior predictive checks as well. So all of it sort of, how do we design these graphical user interfaces to make people act a little bit more, like we want analysts to act, where they're really interrogating underlying models that might have produced that data. And so to conclude, I'll just say a little more. Hopefully I've convinced you that we need more theory and visualization, or at least that it opens up this productive space for thinking about how to make our tools better. But I think there's more that could be said about what is still vague in visualization research, and probably research in general in sort of supporting interactive data analysis. So I see a big gap, for instance, when it comes to formalizing the problems that we study and the approaches that we take more broadly. And there's really a question, is all this trouble worth it? We focus on trying to get the interface right, the visualizations right, but how do we know when it's actually valuable to spend a lot of time thinking about the visualization for some data analysis tool? And so I think a first step here is getting clearer on what types of inference problems we are trying to address with visual interfaces for data analysis. And so I think of this sometimes relative to what's called the anthropic principle, kind of loosely in statistics, which is this idea that we only need statistics for certain types of problems. So if the signal is huge relative to the noise in the data, then we don't really need statistics because it's going to be obvious. Maybe visualization, is important there. We can just use a visualization. We don't have to run any sort of tests. On the other hand, if the noise in the data is or the amount of confounding is sort of overwhelming of the signal, then, we could try to use statistics, but it's pretty hopeless. We're not going to be able to separate out the noise to really get at the signal. And so this implies that there are certain types of problems, sort of in the middle region where there's some noise and confounding, but there's also, some signal where we can use statistics and expect to benefit. And so I think that's really a relevant question is, well, where does visualization fall in this middle region? Are there, some problems where we could use either just visual analysis, or we could do statistical modeling, or we could do both and we're fine? Do we need both of them for other problems? Like we actually must have statistics in addition to visualization? Are there some where visualization alone is okay? And I think if we look at visualization research and research on interactive data interfaces, I think a lot of researchers would have trouble actually pinpointing, what kind of problems do we think we're addressing? And so another reason I think I find this interesting and potentially important for future work is that whenever we think visualization alone is useful for solving some data problem, then we also probably think, or we should think, that the intuitive strategies that people are using are also sufficient for that data problem. And so things like, this what I call visual empirical optimization, these kind of mean distance heuristics. I don't think we know a lot yet in terms of like, how robust are these strategies? So if you defined kind of the perfect rational agent, and then you compared how they would do on some data task versus how some of these strategies would solve that same task or make that same decision, how close are these things? Maybe we don't need to worry about visualization in as many settings as we think we do. So anyway, these are all kind of, unanswered questions I think about that I think can help us sort of formalize and better, explain what about visualization is so useful. So I have plenty more I could say on this topic, but for now, I hope I've at least gotten you interested in thinking about theories of inference for interfaces. So thanks for your attention. I'm happy to take questions. I have to also just acknowledge all of the PhD students I've worked with, RAs, collaborators on all of this work. So thanks for listening, and thanks for inviting me.
Thank you so much, Jessica. Yeah, actually, Brooke is just chatting to me about how cool he thinks your work is. Any questions from the audience? So from Haley James, thanks so much for sharing this fascinating work. In the context of these types of experiments, what's the role of teaching participants to use a type of visualization? Similarly, have you found visualization methods that are worse by comparison generally, but are better after teaching users how to use them, or for certain cohorts of users?
Yeah, no, I think that's a super great question. So when we, do these experiments, especially with new uncertainty visualizations, and especially when we do them for non-expert populations, or we test there, because we've done both, people who are actually more familiar with statistics and people who aren't, how we initially instruct them on how to use the thing, or just the information we give them before we study their decision making is super crucial. So, it doesn't often, it's not like part of the research contribution, but how do you take something like hypothetical outcome plots or random draws from a distribution and explain that to someone, who maybe can think about uncertainty in terms of like we measured multiple values from different people, but might have a much harder time thinking about, like possible worlds. So we do have to think a lot about that. And I think in using these techniques in the wild, there's a lot of thought that has to go into how do you explain them sort of simply, but in a way that cuts down on people's, misinterpretations. We've had also interesting results, though, when you look at things like some of these better uncertainty representations, or I shouldn't even say better because results are mixed, but some of the ones that try to give you more of an intuitive or experienceable sense of uncertainty. So things like hypothetical outcome plots that are animated. We have found that sometimes using these to do some task like judging, which of multiple models might have generated my data samples, can lead people to then perform better with worse visualizations. So we did a study where people were judging, they saw hypothetical jobs reports, so annual jobs numbers by month, and they had to say which of multiple models, like a steady growth model or a no growth model produced that, was more likely to have produced that. And we found that they actually, after using the hops, did better on this task with error bars. And so I think there's a lot of interesting things there, particularly with, rolling these things out, explaining them well initially, but then, just trying to get people a little more accustomed to them. I think you might see more benefits, if people build up sort of some sense of like, what does uncertainty look like? And so it's challenging though, because, it is overwhelming, especially when people are working with data, they're already sometimes overwhelmed or cognitively overloaded. One other thing, what was I going to say? And this latest work we're doing where we're trying to build this Tableau system that also helps you kind of, check models. I think it's a huge question there, how we, which I alluded to a little, but how do we get people who, want to do better in terms of checking their gut instincts about, what factors are important in the data? How do we get them to actually learn how to look for deviation and how to judge different types of deviation from model? Because it's not always obvious, what a statistician looks like when they plot model predictions against their data. It takes time to develop those skills. And so I think it's an interesting sort of design opportunity, because we can think about, well, how do we give visual annotation and visual guidance so that these kind of skills become a little more ingrained? Great question. And then I think the final part of your question was about different audiences, right? I think I haven't done a lot like experimenting with whether you should teach things differently. Most of the time when we do an experiment, we're either looking at like the more experts or the more novice users, but I would expect that, if you're building like a visual analytics tool, like we're trying to do, you have to think carefully about like, how do you judge what kind of user you have so that you can give the appropriate amount of scaffolding? So yeah, that's a great question.
I think Burke has a question. Burke, go ahead.
Yeah, sorry. So just like kind of to go off of this teaching theme, like another thing that I'm curious about is for some of these visualization experiments that you spoke about, like, do you find that there is, I guess, significant differences across users in the way that they interact with the visualization? Like, so, I mean, and the reason why I'm asking this is, I guess, you could say like, oh, this visualization technique is better than this one for this particular problem. But there's also this world in which you like let people choose the visualization technique that's best for them.
Yeah. No, I think
and I don't know if it's worth doing that, right?
Yeah, no, I think it totally is. I'm just thinking of some of the Bayesian cognition stuff we did, where even in like a general sample, like on Mechanical Turk, when we looked at like this bias toward under updating your beliefs, like we showed you huge data sets and people on average under updated by a ton. But there was like huge difference just within that though. When we showed a better uncertainty visualization, some people, it made a huge difference and suddenly they realized how much data there was. On average, it went up, but like the average was a terrible descriptor of like the actual, some people didn't benefit at all and some people did. And so I do think, like that's, something that, I think visualization tools already do that to some extent. Things like Tableau already have like this analytics pane where you can start adding trend lines. I think the difference between what I'm trying to do is that, if we're going to be giving people optional sort of extra support, we should try to take it out of this purely visual realm. Because I think a lot of people, who use things like trend lines and the slightly more sophisticated things in Tableau are still seeing it as mostly a visual tool. And I just want to, they're not thinking deeply about the underlying models. And so yeah, there will be big differences potentially in how you introduce these things to different people and whether they're useful. I think the big challenge with what we're doing now with showing people model predictions is that, until we test it, we really don't know how badly we can fail, like how badly we can confuse people, or, we might make it worse for some users by showing them something that they just cannot grasp what we're showing them. So it's tough.
Cool. Thanks.
Yeah.
David?
Apologies in advance if there's a loud noise behind me. There's workers in the house. So a lot of models are now being used as input to a human decision maker. And so there's, I think, a widespread view that we can sort of separate it into two pieces. There's taking the algorithmic taking the algorithm output and visualizing it for the human decision maker, and then the human decision maker making a judgment given whatever they extracted from the visualization.
Totally.
And so I'm wondering, do you have you done experiments on, or do you have thoughts about the likelihood that there might actually be interactions, which is that it's not separable in this way, where the sort of intermediate cognitive state of, oh, I understand the uncertainty, or I don't understand the uncertainty, might or might not sort of screen off the algorithm's influence on my decision making? I apologize if that doesn't make sense, but it's sort of, there is a very stepwise picture, I think.
Yeah. I mean, I think the problem is that often people, like, it's hard to tell whether like the procedure for extracting data from a visualization is something that is like at the level of like a perceptual bias, where like it's not something someone could actually say even. It becomes harder to isolate it experimentally as well, versus, you know, it's something that you could train them out of. I'm very interested in this, like I'm doing sort of a theoretical project now, where we're trying to sort of get more formal about these different strategies for like extracting information from visualizations. And in particular, like thinking about a visualization as sort of like an estimator, like a statistical estimator, where it's not, you can't necessarily even say for a given visualization, like what's the class of extraction strategies that might be used, but like how do we begin to predict this kind of thing? Because I think sometimes, you know, the most surprising results I've seen are where you're giving someone all the information they theoretically should need, and like they should get, and there is some layer where they're extracting. So yeah, I don't know that I have anything deep to say, but it's something I think a lot about.
So Rajesh Gupta had to leave early, but he wanted me to bring forth this comment of his. Thank you for the great talk. We will appreciate reference to your best students in the area who may be on the faculty job market.
Yeah, so yeah, I have a student graduating now, and I will definitely tell him after today that he should check you guys out, and a few more in the pipeline, so for sure. Yeah. And thank you for inviting me.
Oh, thank you for the great talk. Sorry, I don't want to cut it short. Any other questions? Okay, not, maybe let's thank Jessica again. And yeah, further questions, we can also reach out to Jessica.
Yeah, feel free to contact me if anybody has follow-up questions. So yeah, and thanks for having me again.
All right, thank you again.
Bye.